This is just a quick heads up. This video is about double a normal video. I think it's about 120 minutes. Well, hello. It's time to start a new chapter. This chapter will be on similarity. Similar objects are objects which look about the same, but they're different sizes. For instance, two squares are always similar. Their sides are always in the same ratios, and they all have the same angles. And we're going to spend a whole chapter talking about stuff like that. One topic at a time, of course. So the first thing we have to understand in order to study similarity and similar polygons is ratios, proportions, and the geometric mean. Yeah, it's a big title. It sounds like a whole book right there, but it's not. Like I've probably mentioned before, you know people with big names who are probably no more complicated than people with small names. Same thing here. This is actually a pretty easy section. So what the heck is a ratio? Well, a ratio is something you're already familiar with. It's really just another way of looking at a fraction. I could say, for instance, odds are frequently put in ratios. If you gamble, oh, wait a minute. Frequently written this way. However, it's just as legitimate to write. There's a very strong connection between fractions and ratios. In fact, if you understand fractions well, you have no trouble at all with ratios. This means 3 over 5. This is 3 to 5. For instance, a totally common use of ratios is in cooking recipes. You can have an exact amount, say 1 cup of this, 2 cups of, let's try it, let's suppose we need 1 cup of A and 1/4 cup of B and 2 cups of C. Well, then multiply through everything by 4 so we get whole numbers. That's usually an easier way to deal with ratios. And so this is 4, this is 1, and this is 8. And we could write this as 4 to 1 to 8 would be the ratio of A to B to C. And all this means is, however much of B we use 4 times as much of A and 8 times as much of C. For instance, if it called for, say, 5 cups of sugar and 1 cup of unsweetened chocolate powder. If you don't recognize that, that's the beginning of fudge, which I like a lot. And the ratios are, the recipes are listed differently, but all I ever remember is the ratios. That way I can make any particular amount that I want. If you ever read a recipe, it gives you exact numbers like 1 cup, 1/4 cup, and it tells you how many servings it makes. Well, if you just rewrite the recipe in ratios, which is what I always do, and then figure out how much you want to end up with and work backwards. So if this made 4 servings and you only wanted 2, you just cut each of these in half. Real simple. Recipes are an excellent example of proportions and how you use them. Working with them, you pretty much work with them a lot like you did with fractions. And this is a triple ratio, which we will see in a future section, but we're probably not going to use it much in this section. I'd have to double check the problems. But when you only got 2, then it works almost exactly like a fraction. Now in this class, a proportion will be an equation which states the equality of 2 ratios. What did he just say? Well, if you write it down, it makes perfect sense. A over B equals C over D. Boom. That's a proportion. Here's a ratio, and we're just saying that they're equal. How can they be equal? Well, remember back in fractions, exactly the same thing. For instance, you remember writing things like 6 over 12, which you could then reduce to 2 over 4, or 1/2. Ratios, much like fractions, usually write in the lowest form. In other words, the reduced form. This is usually the preferred way to write the ratio. Just like with fractions, you tend to reduce them to their lowest form, their simplest form. Or put another way, when it can't be reduced anymore, it's reduced to its simplest form. But the important part of that is just remember that when we write something like this, a relationship between two ratios, we call that a proportion. Got a whole separate name for this little equation here. Speaking of equations, we've also got names, naturally, for quantities which we can derive from this equality. What did that just mean? Well, what I'm talking about here is something called the means, which is this and this. And if I write it in the it's not a semicolon, it's a full colon representation, which is be something like the equivalent to these parts here. These are called the means, and these are called the extremes. Writing it this way might make it more obvious how they got their name, I guess. This is the 2 in the middle, and this is the 2 on the outside. If you write it this way, then you have to remember that the product of the means equals the product of the extremes. Or, if this were a fraction, you could, let me rearrange this. We can write AD equals B times C. If you write it out this way, this is very easy to derive. In fact, why don't we do that? It's not much to it. Let's say we've got A over B equals C over D. Now this is easy. How about we multiply each side by D? The multiplication property of equality, right? That leads to dA over B equals CD. Now, how about we do the same thing with B? We multiply both sides by B. I could stick it in here. I was getting a little too sloppy. Multiply each side by D, and what we get is dA over B here equals C. Well, now we can just take this equation and write dA over B. Oops. That's an equal sign. And that's supposed to be a B. Jeepers. Now let's multiply both of these by C. Each side by C. Pardon me. Multiply each side by B. And just slow down and talk right. And what does that give us? dA equals CB. Well, isn't that what we started out trying to show? Yeah. And you probably knew that already. After all, you could probably do that in your head in just a second or so. Multiply through by D, that gets rid of it on this side and puts one over here. Multiply through by B, gets rid of the B in the denominator here and puts one over here, and you get dA times BC. Or pardon me, dA equals BC. And by the way, everything I've done so far, we're assuming b not equal to 0 and d not equal to 0. And all through, we're going to assume that the denominator is not equal to 0. In previous videos, we've shown what happens when you let 0 sneak into your denominator. Lots of things go wrong. Actually, not lots of things. Everything goes wrong. For this section, there is one more thing we need to know. It's called the geometric mean. Remember the regular old mean? You know that. Say two numbers a and b, we get a plus b over 2. Well, the geometric mean, I'll call it GM for now. That is a times b, and then we take the square root. There's a certain sense to this. For instance, if we had a plus b over here, if b turned out to be equal to a, so it was a plus a, that would be 2a divided by 2, and that would just give you a. And that kind of makes sense. You would expect the average of a and a to be a, wouldn't you? Well, if b was equal to a, we'd have a times a, which is a squared, and the square root of a squared is a. So, there's a sense to this, even though it looks kind of weird. And there's another way that this is defined. It's frequently written this way, just in case this doesn't confuse you, we can do it this way. Maybe now you'll get confused. The geometric mean is the number which makes this statement true. In other words, we got a over some number is equal to that same number over b. What is that number? Well, it turns out that number is the geometric mean. Or, the name we give it is the geometric mean. I would say that it turns out that number is the square root of the product of the extremes. So what we have here is, if we insert this for x substitute, we get a over square root of ab, and here we get square root of ab over b. There's lots of ways we could show this is accurate. One thing we could do is just cross multiply. Square root of ab times the square root of ab is by definition ab. And when we cross here, we get ab. Or we can just simplify the expression. Square root of a goes into a square root of a times. The number which would make this true is the square root of a times b, and it's easy to see if we reduce these fractions. Square root of a goes into a square root of a times. That gives us this. On the other hand, we can divide top and bottom by square root of b, and this drops out, and this becomes square root of b. And we end up with square root of a over square root of b. And both of these are, of course, equal to that, square root of a over b. That's legal. The other thing you could do is just square both sides. Let's say we're going to only talk about the positive square root here. Then the square of this is equal to the square of this as long as these are both positive. No, actually, even if they weren't both positive, they'd have to both be equal, and then the squares would still be equal. Either way, we can square both sides and get down here a squared over ab, and the a's cancel and we get a over b. And here we get ab over b squared, and the b's cancel, and again we get a over b. But since we squared both sides, now we take the square root of each side and get the square root of a over b equals the square root of a over b. So there's three ways you can show that this makes sense. That the square root of a over b is the value of x which satisfies this equation. You can probably find other ways to do it. It's not very, very complicated, really. Well, that introduction to ratios, proportions, and geometric means took way too long. Seems like that always happens with the first section of any chapter. A lot of new stuff, I guess. Well, let's work some problems. The measures of a triangle are in the extended ratio. I think I mentioned before we can have 3 numbers, not just 2. And when you've got more than 2, it's called an extended ratio. It's no big deal. Now, we're going to find the measures of the angles of the triangle. We know what their proportions are. And just like any problem like this, we need to know something about them. Well, what we know is that these angles add up to 180. And since these are, you could actually also think of these as units. It would take 3 of something plus 5 of something plus 10. If they were inches, it would be 3 inches to 5 inches to 10 inches. Or feet, 3 feet, 5 feet, 10 feet. In this case, it's degrees. And it's broken up as 3 to 5 to 10. So all we have to do is break up 180, well, this way. It's 3x plus 5x plus 10x. What's the x for? Well, that's a multiplier, because if we think of these as degrees, this is 3 degrees plus 5 degrees is 8, plus 10 is 18 degrees. Well, that doesn't add up to 180. However, if we multiplied each one by 10, I bet it would. Let's check. And after all, these 3 added up to 18, right? So if we multiply each one by 10, I'll be amazed if they don't add up to 180. It'll be 30 plus 50 is 80 plus 100 is 180. I suppose we didn't have such nice easy numbers like that. How would we work that out? Well, we just do, in a sense, the long way what we just did in our head. 3 and 8 is 10. So we got 18x equals 180. Now, x obviously equals 10. Just divide by 18, you get x equals 10. And that means that this is 3 times 10, 5 times 10, and 10 times 10. What you have to do when you're figuring out how to spread these numbers out across a given total is to set it up like this. What you're always doing is finding a multiplier out here. There's some number you're going to multiply each one of these by to end up with the total that you're given. Let's work some more problems and you'll see what I'm talking about. It's really pretty easy. Let's do one more like that just to show that we really do know what we're doing here. Again, the angles. So let's pretend these are degrees. Now this is reduced, just like the previous one. In the previous one, the unreduced would have been 30, 50, and 100. Instead it was 3, 5, and 10. Here we get 2, 7, and 9, which adds up to 20. No, pardon me. That's up to 18. Cheapers. My calculator broke. It adds up to 18 again. So once again, we're just going to multiply by 10. Gee whiz, I shouldn't even show us in this problem. We're going to do exactly the same thing. We write 2x plus 7x plus 9x equals 180 in order to find x. Well, we got 2 and 7 is 9 plus 9 is 18. You get 18x equals 180. And we're back to x equals 10. Now these don't add up to 18. You watch me do it the last 2 times, writing 11x plus 12x plus 13x equals 180. Do I have to write it out that long way before I add it up? Why can't I just go 11 plus 12 is 23 and 13 is 36? And just directly write that 36 times something equals 180. Why? Remember, the angles have to add up to 180. These are the proportions. So we're going to have to multiply each one of these by some multiplier, and it'll be the same in each case because you have to maintain the same proportions. We can't like multiply this by 8 and this by 10. You can't do it that way. Whatever number we come up with as the multiplier, it has to be the same all the way across. For instance, in this case, so in this case I can write 36x equals 180, divide through and get that x equals 5. So our ratio should be 55, 60 to, that's 65. 5 times 10 is 50, plus 50, yeah, 65. Do these add up? I hope so. See, 55 and 65, that adds up to 120 plus 60. That's 180. Okay, it works out. So I think you see what we're doing here. When we have to jack these numbers up to get them to fit into some total, these are the reduced ratios. Now we have to unreduce them, so to speak. We got to go back the other way. For instance, if you were given these 55, 60, and 65, you're given a triangle and asked what are the proportions, or pardon me, the ratios of the angles. Well, you would write it out this way and then reduce it. Of course, in this case, you would find a common factor. In this case, 5. And you'd write 55 divided by 5 is 11, and you couldn't reduce it anymore. And that's how you would arrive at the 11, 12, 13, given this situation. On the other hand, if you start out with this, then you go backwards and come up with the actual angle measures. Well, this one not only involves ratios, but you have to keep in mind something really simple. Another one of those big names that doesn't mean all that much. It's called dimensional analysis. And that's what this person got wrong, if it was a person. May not have been a student. Could have been a polar bear trying to figure out where all the seals were. If that's the case, he went hungry. Why? Well, you can set up dimensions very much like fractions and then cancel them. For instance, I would probably just insert 36 inches in here and simplify the ratio from there. But technically, to convert 3 feet to inches, what do? You write 3 feet times 12 inches per foot. Which of course is going to, now what happens is the feet cancel and you get 3 times 12 inches. What was the mistake here? Well, he tried to multiply this entire ratio by 12 inches per foot. That's incorrect. If you're going to write this, then what you really have to do is write it out this way. 8 inches times 1 over, because this is the part that you multiply by 12 inches over 1 foot. So it would be like this. And now you can leave out the 1. It's inches per foot, 12 inches per foot. Now the 2 foot symbols, you can cancel them as if they were actual numbers or variables. It's part of dimensional analysis, and if it didn't come up in algebra before, it's extremely simple, and it's a really easy way to keep track of your units and make sure you're not messing up the way this person did. So if you do it this way, then you get, you could flip this, because that's what actually happens. 1 over a fraction is just the inverse of that fraction. So I can go ahead and write it that way if I wanted to. Times, and now we have to invert that. Why? That's inches. Well, let's look at it this way. What's 1 over A over B? Well, that just equals B over A, doesn't it? You just flip this. Same thing down here. 1 over 12 inches per foot is the same as 1 foot per 12 inches. The other way you could spot this is that the ratio should end up without any dimensions. For instance, if you had 8 inches over 36 inches, you could cancel the inches. And that makes sense because ratios frequently don't have to have any units. The units, in a sense, drop out. You figure out what the units are. Like what we did before with a triangle and the ratios of the angles in the triangle. Suppose it didn't add up to 180. Suppose we weren't using degrees. We could have used radians, in which case we would come up with a completely different multiplier, but the ratios would still be the same. So it wouldn't matter whether we use degrees. In fact, the same thing's true here. We can convert this to inches, and we'll get a new ratio. We can convert the inches to feet, and we'll get a ratio. So the proper way to convert this is, you can write it out like this if you want, and then flip it. Or you could just keep in mind that the standard conversion is inches per foot. If we want to get rid of the dimensions, it would make sense to put foot per inch over here, which would again tell us that we got 1 foot and 12 inches. Any way you slice it, the equation that we should end up with, let me give myself some room here, should look like this. 8 inches over 3 feet times 1 foot per 12 inches. Again, that way we can match up our units and cancel them. Cancel out the feet, cancel out inches, and we get 8 over 36. And when we simplify 8 over 36, we get 2 over 9. Most of the time in ratios, it's better to simplify it. Drop it down to its lowest form. Suppose we didn't want to do it that way. Say we don't like this. Maybe you don't like inches, you want feet. Well, you can do that too. We write it this way. Right, 8 inches over 3 feet. But now what we want to do, suppose we just converted this to feet. What would this be? Well, that'd be 3/4 of a foot, right? Over 3 feet. Well, pardon me. Got an equal sign in there. The feet cancel. And what does this turn out to be? Well, speaking of bonehead moves, I wrote 3/4 in there. That's just dumb. It's 2/3. 2/3 of a foot is 8 inches. 8 inches, 12 feet, you put 8 over 12, and that reduces to 2 over 3. And this fraction, or proportion, reduces to 2 over 9. That's because whether you convert the numerator to feet and then take the proportion, or convert the denominator to inches and then take the proportion, the proportions need to be independent of the units. Keep in mind when I say independent of the units, I don't mean to say that you can mix them up. You can throw inches and feet and miles and kilometers. No. You have to put everything. In this case, all the numbers, the top to the bottom. If it was an extended ratio and we had 3 numbers, each of those numbers in the ratio had to have the same units attached to it. So we can convert this one to whatever this is. We can convert this to whatever this is. But we can't mix them up. And when I say that it's unit independent, I mean once you've matched up the units, at that point it doesn't matter which units you used. You can match them up as inches, match them up as feet, match them up as yards. You could use these would be very tiny fractions of a mile. And if you converted these 2 measurements to miles, you would still get 2/9. Yeah, this one is going to be related to the first one we did. The measure of the adjacent interior angle, the ratio of the measure of the adjacent interior angle to the exterior angle is 1:4. Well, if we set this right algebraically, we should have, remember, A and B have to add up to 180. This is a straight angle. A would be your exterior angle, and B is the adjacent interior angle. These two together form a straight angle, so they add up to 180. So this, we just have to find a multiplier that makes these two add up to 180. That's pretty easy, really. 1x plus 4x is 5x equals 180. Or, what do we have for x? So we have to multiply by 36. Remember, this is the measure of the exterior angle to the interior angle. So this is A over B. That's equivalent to 1/4. This is the 1 and this is the 4. So that means this is 36 degrees. And this would be 144 degrees. So the other thing this means is I drew this completely wrong. This angle here, this is 144 degrees. That's should be more like this. That's 144 degrees with this, and then we get this really weird looking triangle where this is the 144, the B, and this is the 36. This triangle that I drew is just something to, so you've got a picture, know what you work with. Keep in mind that when you're drawing a picture to begin with, you don't know how accurate your picture is. And you have to be willing to accept the fact that you drew your picture completely off from what was really going on. This picture really has absolutely nothing to do with the real situation. However, it's good enough to set up the algebraic equation, at which point you should forget about this picture because it is totally inaccurate. Oh, and I almost forgot to mention, if you're curious, the answer is that the triangle is obtuse. We found this angle here, which is an obtuse angle. Well, here's an easy one. You can probably do this in your head. What's the perimeter of a square? It's just this, add up all 4 sides. But with a square, that's particularly easy. Suppose the length of this segment is A, well then they're all A. That's what it means to be a square. Every side is congruent. So the perimeter is obviously 4A. The length of one of its sides is A. So if you write it perimeter, the ratio of perimeter to square, it's 4 to 1. Or if it's, pardon me, perimeter to side, it's 4 to 1. If it's side to perimeter, it's 1 to 4. I think the way they asked it, I think the answer would be 4 to 1. Yeah, here's one that's not too bad. You can probably just about do this in your head. We got that the ratio of AB to BC, there's AB here, here's BC here, is 3 to 8. So we could write that the ratio of P to 24 equals 3 to 8. So let's use our property of proportions. Remember, the product of the means, that's the inside part here, equals the product of the extremes, which are the two extremes. Okay, so we get 3 times 24 equals 8 times P. And this is 3 times 24 is 72. Multiply through by 1 over 8. And that is P. And of course, that equals 9. So P over here would turn out to be 9. Does that work? Is the ratio? Remember, we can write them this way, or we could write them like this. Well, if we simplify this, what do we get? 9 divided by 3 is 3. 24 divided by 3 is 8. Looks the same to me. Remember, 3 over 8 can be written as. We can switch back and forth between the fractions and the colon proportion symbol. Yeah, here's one that doesn't look like you could actually do in your head very easy. But we just need to use what we learned about proportions, or pretty much what you already know about fractions. We'll just cross multiply here. 5 times this and then 4 times that. And then this. So we'll end up with 2 different sets of equations, which is good because we have 2 variables, and if we only had 1 equation, we'd have a problem. So if we take our products, by the way, if in this course this is called a cross product, where you take the product of the means and set it equal to the product of the extremes. We call that a cross product in this course. In other courses, the cross product will be defined a little bit differently. If we do that, we get 5 times this down here. Use our distributive property and get 10a minus 5b, and set it equal to 4 times this here, which is 4a plus 4b. So what do we have? We subtract 4a from each side, add 5b, and get 6a equals 9b. Or we can write this as b equals 6 over 9 times a. We could reduce this to 2/3, but notice we've got a 9 over here, so let's just leave it in ninths, and maybe things will drop out nice and easy for us. Now that we have an expression for b, we have a second equation here. So let's substitute that expression in here, so everything is in terms of a. So over here we get 9 times 6 over 9 times a. We're just substituting in our expression for b here. And that's 5a plus 45. This, of course, reduces to 6a. And if we subtract 5a from 6a, we'll get that a equals 45. And they asked us for a and b. Well, let's see here. We got a is 45. What about b? Well, we got a couple equations here we can use to find that. For instance, but I think the one over here is probably the easiest one. If A is 45, then all we have to do is take, well, we already know this is really 2/3 of 45. Well, 3 times 15 is 45, right? 15 times 2 is 30. So this whole thing turns out to be 30, and that means that B is in fact 30. And there's your answer. Just keep in mind, whenever you see two variables, you're going to have to come up with two equations. If you want to solve for both variables. If you want to solve for one variable in terms of the other, like we did right here, you can always do that. We can solve for B in terms of A. But if we want to attach some actual numbers to these variables, we're going to need a second equation. And that is why it's not a coincidence that they gave us two equations here and two variables. These guys are smart. They know what we need, and they gave us everything we needed to solve the problem. Here's another one that's probably not too easy to do in your head. But let's take advantage of the fact that these two expressions are both equal to 24, which, by transitivity or substitution, whichever way you like to look at it, we can set this equal to this. What good does that do? Well, we'll see. Well, if I write this all out, probably the first thing to do is put all these in terms of a common denominator so we can add them all up. Don't know if that'll do any good, but it's probably a good start since we have addition signs here. So our common denominator would be x times y. It would be 5x over xy, 7y over xy, and so on. Now with all these common denominators, yeah, we could add them up, I guess, and write 5x plus 7y over this equals 12x plus 2y over this. But when the denominators are the same, you probably already know from algebra that the numerators are equal. So all we have to do is set the numerators equal. In other words, it's the same all the way through. Or there's an easier way to look at it, I guess. I just automatically look at that and say, well, just throw all that down and use the top line. But if you haven't been doing this for 100 years, it might make more sense to multiply by xy on each side. Remember, it's like the distributive property is going to operate on this. So it's not just this expression that will get multiplied by xy, it's everything on this side. So we do that and we cancel out the xy's all the way across by multiplying by xy on each side. And we end up with 5x. Well, there's supposed to be an x in front of there, pardon me. I'd do that over, hang on. There we go, 5x plus 7y equals the 12x plus 2y. Well, let's suppose we subtract 5x from each side and get 7x over here. Subtract 2y from each side and get 5y over here. Now, multiply through by 1 over 7 and 1 over y. In other words, multiply through by 1 over 7y on each side. So over here, the y's will cancel and we'll get 5 over 7. And over here the 7's cancel and we get x over y. Well, I think that's what we were looking for, right? The ratio of x to y. And the answer is 5 over 7, or 5 to 7. Merely just a bunch of algebra. Well, here's one if you like gears. Even if you don't like gears, we've got one. This involves gear ratios. And they pretty much explain what a gear ratio is. Number of teeth of the larger gear, like this to this, or this one to this one. For instance, it sounds to me from the way they've written it, like the largest one is gear A, and the smallest one is gear C. And we don't know how many teeth gear B has, but they say that the ratio of A to B is equal to the ratio of B to C. That doesn't mean that these are the same gears. It just means that the ratio is the same. Just as 8 over 16 is the same as 4 over 8, which is the same as 2 over 4, which is the same as 1 over 2. If those were gear ratios, they'd all be different gears with different sets of teeth, but they would have the same ratio. So let's just let A represent the number of teeth on gear A, and B the number of teeth on gear B, and C the number of teeth on gear C. What they tell us, if we rewrite this algebraically, is that the ratio of A to B equals the ratio of B to C. And remember, we can also write this, if it makes the algebra any easier for you, like that. These are equivalent. Whichever one you think makes it easier for you to see a way to solve the problem. Now, remember, the product of the extremes equals the product of the means. So we could start with that and write that B squared equals AC. But aren't we given actual numbers for A and C? Yeah, 36 and 16. So we can put those numbers in down here. Now we can multiply this out and take our calculator, figure out what this is, and then take the square root. But since this is B squared, I can now write that B equals, and it's going to be the positive square root, of course, because a negative number of gears really doesn't make sense. Well, this happens to be a perfect square, and this is a perfect square. In other words, this is the square root of 6 squared times 4 squared. And, of course, this is just 6 times 4, or 24. So, B equals 24. And it kind of makes sense. Well, let's see if it makes sense. Let's not say it makes sense. Let's check it out here. What about 36 over 24? Yeah, we can just rewrite this here. 36 over 24. How does that compare to, just put a question mark there. We don't know yet. Could be bigger, could be less, could be equal. What's the relationship? How does that compare to 24 over 16? Well, we could divide both of these by, down here we could reduce this by dividing both by 12, and we get 3 over 2. This is the reduced form of 36 over 24. What about 24 over 16? Well, suppose we divide through by 8 with both. Divide 24 by 8, divide 16 by 8, and we get 3 halves. So, we have an equality, which is what we were looking for. So we seem to have the right answer. Well, here's one where it seems like we can ignore one piece of information and zero in on the other, or vice versa. In other words, they're telling us that the length to width ratio is the same for each piece of paper. So, let's use that and see if we can just use that to figure out what x is. Let's take width over length as the ratio. Or we could write it like this, the ratio of width to length. Or let's write, just for fun, let's make it W over L. Well, in that case, if we use this representation, W over L would be 297. Go over X. And over here, W over L would be X over 594. Now, first thing we should check, I didn't include the units in here, but I am going to double check and make sure that they are the same. Millimeters, millimeters, okay. If they're not the same, then you need to convert things. When you want to get proportions and ratios, you want the units to all match up. A ratio which is inches mixed up with feet, or feet mixed up with miles, that doesn't make any sense. Well, I guess it could make sense if you specify ahead of time the ratio of feet to miles is this, like in a scale map, in which case it does kind of make sense to say it that way, because in fact inches to miles is more often. 1 inch could equal 50 miles. But usually when you're coming up with these ratios, you want to try to match up the units, and if you don't match up the units, be sure to point out that they are two different units. Don't just throw in numbers like I did here. Okay, now this, obviously, as we know now, implies that the sum of the product of the means, that's x squared, equals 297 times 594. So of course x would be the square root of that. May be obvious to you what that is, but I think I need a calculator. And if we go ahead and write this out, you have your calculator, and you should get that x equals, whoa, what the heck number was that supposed to be? How about, it's like 420 point something or other, 01. Let's just round it off to 420 in terms of millimeters. 100th of a millimeter isn't very big. Well, I think the reason it works out so odd is these may have been initially in inches, but I could be wrong about that. I have seen these paper sizes, you probably have too. When you use the print menu on your computer, where it says paper size, if you open that up, there's a whole bunch of them. And a lot of them aren't listed by dimension, they just have numbers like A5, A3, A2. It's up to you to figure out what that means. What was the other way to do this problem? Well, it leads to exactly the same thing, which makes sense. If you're going to get the same answer, it should, at some point, lead to the same calculation. What is the geometric mean of two numbers? Like the geometric mean of A and B is just the square root of A times B. So this is the, we'll call it the geometric mean. Well, instead of doing all this, I could have just recognized the definition of a geometric mean, which is the square root of the product of these two numbers. And then you take the square root of that. Well, that's just what we have right here. So we could have just immediately written this part down without recognizing this. They actually, I would say, gave us more information than we needed. Consequently, we have two ways to arrive at the same equation and, of course, the same answer. Here's one I like, for the same reason I like the last two. They're using things that you're probably familiar with. Trying to point out that this is not just a bunch of disjoint nonsense that nobody will ever use and has nothing to do with any kind of reality you will ever be part of. That's not true. This is actually part of your reality. I admit that last chapter, chapter 5, with the angle bisectors and perpendicular bisectors and mid-segments, and altitudes. That all seemed a little out there, didn't it? I mean, it seemed kind of spacey and not very useful, and things that you wouldn't see on a daily basis, things you may not even see on a monthly basis. I think this chapter is quite a bit different from that, and hopefully should be easier for you. I think it's simpler to use things that you're a little bit familiar with. It adds a reality to the problems you're working on. Most of Chapter 5, heck, we could have been talking about something going on Mars just about as well as here. Not all of it, but I'm sure a lot of it seemed that way. So now we got batting averages, which I'm sure you're all familiar with, and you probably already know what they are. But suppose you did want to know how many hits your favorite player actually got. The average is easy to look up if you don't happen to have his baseball card. And what we have over here is that .304, his average. We don't have to put the 1 on the bottom. Anything over 1 is just the same thing. It doesn't change anything. In other words, A over 1 is the same as just writing A. It's no difference. Number of hits, that's what we don't know. And the number of at-bats was 621. So, if we had a 1 down here, we'd write 1 times x equals 621 times 304. But I think you guys are smart enough to figure out that there's always a 1 down here if you want it to be. So, it's just x equals 621 times .304. Looks like you hit a little over 180. 190 or so, but let's work it out exactly. So, all we had to do was multiply the .304 by 621 and get 188.78. You can't go to bat a fraction of a time. At least I don't think you can. I don't know. I don't know how that works out. Step up to the plate, take 2 pitches, and then go into the locker room. I don't know how they call that. But I think 189 is probably the right answer. This batting averages, the fact that they give you the number of hits, that brings up an important point in averages. Suppose a guy has a 500 average. I mean, that's huge. That's superhuman. I don't think anybody's ever had that high an average. At least not anybody who actually played much. But suppose he did have a 500 average. The first question you should ask is this right here. How many at-bats did he have? Suppose the answer was 2. That means he got 1 hit and say he struck out once. Well, that gives him a 500 average. That doesn't make him a great batter. He was only at bat twice, and he got lucky and got a hit. So whenever you see averages, think about the numbers. And there are other things that you need to think about when you look at averages. For a baseball player, the batting average is actually usually pretty good because they normally have quite a few at-bats. But there are other forms of averages. You should always, whatever you hear average, don't take it at face value. The old governor of Washington State, Dixie Lee Ray, pointed out, the average person has 1 breast and 1 testicle. Whenever you hear an average and are tempted to take it very seriously, just remember what Dixie Lee Ray said. And if you don't understand what I just said, ask your instructor about it. He can explain it pretty easy. And here's a interesting problem. It uses population growth. That's good because you're going to see population growth problems probably as long as you're in school. I mean, if you study anything that, well, heck, I don't know. History, sociology might use it. You'll definitely use it in biology, chemistry. Of course, you're not talking about the population of living things in chemistry. It could be crystal growth or something else. But population growth, one way or another, is going to come up. over and over and over, and maybe even one more time than that. So first, what are they saying here? That the population of red-tailed hawks grows by 2.7% each year. Now, if we write this ratio out, 2.7%, that's like, we're the same as 2.7 over 100. But that's the increase. So let's try to get this into whole numbers so it makes sense. Since we didn't add 0.7 hawks for every 100, or 2.7 rather, but suppose we write it as 27 over 1,000. Now we've got whole numbers. We just multiply this by 10 and this by 10. So we get 27 over 1,000. That's the increase in 1 year. So what is the ratio of year n to year n minus 1? Well, suppose we started with 1,000 hawks, and that's an arbitrary number, but we have the increase per 1,000 here in whole numbers. That's the only reason I'm using 1,000 down here. We could say the increase per 5,000 and multiply this by 5, but put 5,000 down here and 5 times 27 down. Up here, we'd have the same ratio, but this gives us whole numbers. Let's just stick with this one for now and see what we get. Well, if we had 1,000 at year n minus 1, our increase is 27 per 1,000. So at year n, we should have 1,027. And at year n minus 1, we had 1,000. So there's our ratio from year n to year n minus 1. 1,027 to 1,000. Now, next thing they want us to do is figure out how many should be around in 2005, given that there are 180 in 2004. Now this isn't too hard. What we have is that well, in this next part, what we do is write out what that ratio actually means. For instance, the ratio here is the number of birds of year n at year n divided by the number of birds year n minus 1. And that ratio has to be the same. Here's the number of birds year n, and here's the number of birds the previous year. And again, we apply our means. Product of the means equals the product of the extremes, and get that x times 1,000. Let's start it right over here. The heck. X times 1,000. I'm tempted to write 10 to the third. You guys probably don't use that notation very often, so let's just use 1,000, I guess. X times 1,000 equal to 180. Uh-oh. So if we leave ourselves room to actually write the equation, we get x times 1,000 is 1,027 times 180. Well, this product turns out to be that. If we divide by 1,000, we just put a decimal point where the comma used to be. It's pretty easy. Just move the decimal. Here's a decimal point here. It would have been like that. Well, move it over 3 places. That's how you divide by 1,000. It's real easy. 0.860, roughly 185, I'm guessing. What was the question? How many hawks, or how much did they increase? They increased by about 5. Okay, and you'd expect to see about 185. That would be the answer over here, 185. You with me so far? You see what we did? probably other ways to do this. By just computing the increase. For instance, this was the increase. If you took 2.7 over 100, or in other words, 0.0027, multiplied it by 180, you should get about 5, and that would represent the increase. You could add that to the original, and you would still get 185. What am I talking about? Well, let's take a look. I'll show you. The over 100, that's like 0.027. What happens when we multiply that by 180? If we had done that, we'd get 0.027 times 180, 4.86, which is much like this, 4.86. We add that to the 180 and get 184.86 or 185. As I've pointed out before, there's usually more than one way to solve a math problem. We did it this way because right now we're studying means and extremes. So let's use what we're studying. But if it occurred to you to just take the original and multiply by the increase and then add that back into the original, you weren't wrong. That's a perfectly legitimate way to do this problem. It just doesn't really use what we're studying right now, that's all. Now we need to do something similar, but it's for 2 years, not just 1 year, which isn't that big a deal. We just do the same thing twice. And afterwards, I think I can show you a shortcut for that sort of thing, if you're interested. If not, just fast forward. What have we got? We got 951 in 2004. Remember, our ratio is that. How many can they expect to see in 2006? Well, we'll do it the way that uses means and extremes first. And then we'll do it the other way and see if we can find a quicker way to make these kind of predictions into the future without having to do it over and over and over. For instance, suppose this is 2010. Would we have to perform this calculation 6 times? Well, I think I can show you a trick that would allow you to answer no to that. Let's do it this way first. Just like before, we have 1027 over 1000 is equal to, let's say, the 1 year population. 1 year from now, over the current population, which is 951, right? So that gives us P1 times 1000. I'm not even going to write that part. I'm going to write this part first. And that's 1027 times 951 equals P1 times 1000. So let's just go ahead and divide by 1000. It's such a simple number to divide by. It's an easy number to throw back and forth. P1 times 1000 equals this stuff on top, then P1 equals this stuff, divided by 1000. That's pretty simple, right? So, all we have to do is, I'm sure you can do this in your head. I'll use my calculator. So I went ahead and worked this out. In actual numbers, if we were only going 1 year forward, we would probably stop right here and round this off to 977, because 0.68 of a red-tailed hawk, or pretty much any bird I can think of, doesn't make much sense. But we're going to use this number in a second calculation. Normally you don't want to round off until you finish all your calculations. That's a good rule of thumb. You start rounding off too early, and then you start to propagate round-off errors, and your final answer is much less accurate than it would be if you wait until the end. It's a good general rule to keep in mind. So, although I think I did one thing wrong here. No, I just rounded off to 2 places instead of 3. That's just because it's easier for my calculator. I probably should have left it as 677. In fact, after what I just said, I'm going to do that. There. now I'm not contradicting myself. And what we have to do is we now put this number in for this one. In other words, so we solve pretty much the same equation once again, and we get 1027 over 1000 is the population at year 2 divided by the population at year 1. In other words, this ratio of year n to year n minus 1 is the same as the ratio of P2 over P1. Now P1 we know, we just figured it out. It's this here. P0 was our starting point, that was 951 here. This is P0 right here. This is P1, and P2 we don't know yet. We plug these numbers in here and go ahead and multiply it out. Yeah, I know, it's a big number. So we get this, and actually it's this whole thing divided by 1000, which, move the decimal point, which is supposed to be right here, over 3 points, and just round it off to 1003. Is there a simpler way to do this? Yeah. It's related to this one right here. Remember I said we could multiply by 0.02. Take, like in this case here, we could take 180. In fact, let's use the other population, the one that was 951. That's even better. So we'll take the 951. That was the Red Hawks in like 2004. And multiply that by 0.027, just like before. Yeah, the dots for multiplication and decimal points. You gotta remember not to get those confused. Now, if we perform that calculation, we get a number here. That equals the increase. So then we have to take the original population, say at time 0, plus the increase, that's this here, and that'll give us the population at the end of the next year. Well, this thing here, especially this part, this whole thing here, is there another way I could arrive at that without actually computing this and then adding in P1? Yeah, it's real easy. Suppose I write 1 plus this population growth number here times 951. What's that going to equal? 1 times 951 is 951, and then 0.027 times 951. Alright, like up here, this would have been 951 here. And the increase, 0.027 times 951, and that equals our new population. That's population number 1. Suppose we apply this again to population, to the next year's population. Okay, remember, this is P1 here. And all this stuff, 0.27 times 95 added to this one here. In other words, 0.027 times 951 plus 951. That gives you the resultant population. This is the increase, and this is where you started. Suppose I write this in general terms, at least for this part here. What do I get? Well, we started with 1 plus 0.027 times, I'm just going to call that P0. Okay? Now that equals P1. what are we going to do next? Well, how about we take 1 plus 0.2027 and multiply by P1. That'll give us P2. Well, that works just fine. But what is this? Suppose, remember our substitution rule or transitivity, either one. Well, I guess I'd go with substitution at this point. That would make more sense, really. If I substitute this expression in here, this expression we have for P1, in here, what's our new expression going to be? Let's try it. We get 1 plus 0.027 times P0 I'm sorry. We got 1 plus 0.027 times, now we substitute. And this is 1 plus 0.27 again. I'm sorry, 1 plus 0.027. I really should just write this as 1.027, but I want you to see exactly how this is working out. By putting this 1 here is the equivalent of sticking the original population back in here after you've computed the increase. This 1 has the effect of adding the original one back into it. That's the whole point of this 1 here. It shortens up taking the increase, that's the increase here, and then adding it to the original one and getting the second year. No, all you have to do is take 1 plus your increase, multiply that by the original, and this whole thing will give you the actual final population without having to add anything back in. The addition happens right here because of the 1 you added to this. That's the effect of this. And it also has the effect of leading to a nice easy equation, because when I substitute P1 in here, I put this in there. So now I have an expression for P2 that doesn't involve finding P1 first. I just take this 1 plus the increase, and then multiply by 1 plus the increase again, and then I multiply by the original population. Notice the first year we multiply by 1 plus the increase. The next year we multiply by 1 plus the increase twice. Next time, guess what? It's going to be 1 plus the increase 3 times. Or, let's just make it 1.027. That's what that actually adds up to. Squared times P0. And so, if you want to know the population 10 years from now, all you have to do is take 1.027 to the 10th power and multiply by the current population, which is much easier than performing this particular calculation 8 times. So if you spot this little trick, you can turn this whole smear of equations into a simple little thing down here. I like things like that. If you do, then I'm glad you got to see it. Well, that's about it for this super long video. Hope you had as much fun as I did.